A child slides down a slide. The weight of the child is 250 Newton. The height of the slide is 7 meter. And the work done against friction, this is important, the work done against friction as the child travels down the slide is 1300 joules. What is the change in gravitational potential energy, and what is the final kinetic energy of the child? So what is the potential energy that he had that got converted, or the change of it, and the kinetic energy? So it's an interesting question. So what is the main point over here is that the kid right now has some potential energy. He's not moving. Once he starts falling, all of this potential energy is being transferred and converted into kinetic energy, but some of the energy is being converted into friction, right? Work done as friction. So that energy is being wasted. That's a fancy way of saying that the effort or the work done or the effort you put in is fighting friction. So if you're fighting friction, you're losing that energy, and that energy is not being converted into kinetic energy. So the total energy converted is kinetic energy, and this work done against friction, so let's call it W work against friction, and F over there, and this is the total energy, right? What do I mean by total energy? Well, you started off with this. Now this is what it's converted into. We know what this value is. It's already said, told to us in the question. It's 1300 joules. We don't know the potential energy, so let's try to figure that out. What's the formula for potential energy? Well, that's going to be mgh. mg, we already know. The mass of the boy is, or the weight of the boy is 250. Isn't that just mg multiplied? Weight is equal to mg. So I know mg, so I'll put that in directly. That is 250 times the height, that's 7. That's coming out to 1750 joules. That's the energy you started off with. So potential energy you started off with was 1750. Kinetic energy, there's no way of finding out because all of the potential energy is not being transferred to kinetic energy. For now, it's not, so it's still unknown, so let's call it Ke still. But the rest of the energy is 1300, right? So looks like a simple equation where I can find Ke, and Ke will be equal to 1750 minus 1300, which should come out to be 450 joules. That's our answer. So looks like A is our answer. Pretty easy. A 300 Newton force is applied to a box to move it up a ramp as shown. So force is going like that. How much work is done by the force when moving the box from X to Y? So they're saying from moving to X to Y, what is the work done? So what is work is actually, work done is equal to the force in the direction that you move in. Right? So if that's being satisfied, let's put in the values. What is the force? Well, they've told us it's 300 newtons. And what is the distance? Well, this is the distance being traveled in the direction of the force. So that's 5. Our answer should come out to be 1500. And the answer is C. Pretty easy. A workman rolls a barrel weight 200 Newton. The weight of the barrel is 200 Newton up a plank of length 2 meter on to a lorry. So you just lifts it up. The back of the lorry is 0.8 meter above the horse. Oh my God. What is the work done on the barrel against gravity? Now this is important. They're saying against gravity. So what is the direction of the work against gravity? So what direction is gravity in? Well, it's downwards. So what would be against gravity? That'll be upwards. So what is the work done against gravity? Well, what is the force required to lift this thing? Well, I'm pretty sure it's going to be close to its weight, right? And that's given to us in the question. So that's 200 Newton. So work equals to, pretty straight sum forward. The force is 2000. And the distance traveled in the direction is 0.8. That's an easy calculation where the answer comes out to be B. 3 objects P, Q, and R have different masses and different speeds as shown in the table. So different masses, different speeds. So what is the order of increasing kinetic energy, smallest to smallest first, of the objects? So essentially we have to put all of these mass and speed values into the formula, half mv squared, right? Pretty easy. So what I'm going to do is tweak this, like you can just put it in and figure out the values. What I'll do is I'll try to do this a little faster, meaning that I'll figure out all the v squared values and then all the m, multiply all of them by m, right? What do I mean? So let's figure out all the v squared values. I know all the v values, these are it. So that's going to be 9, 4, and 1. And multiply each of these by mass. So that's still going to be 9. This is going to be 8, and this is going to be 5. Now I can multiply with half, and what that's going to do is I'll get 4.5, 4, and 2.5, but the order will remain the same, right? As in smallest, because I don't need to know the values, I need to know the order. So it seems like this is smallest, second smallest, third smallest. So it's RQP. The answer is D. Kind of a straightforward question. They've given us the potential energy, gain in potential energy when the weightlifter lifts the mass. So they're asking if this is the energy, what is the mass? So again, it's mgh, and the mass is unknown. The gain in potential energy is 4500. G is 10. The height it went up by is 1.8. Simple calculation. Your answer will come out to be B. Over here, they're trying to ask you literally the definition of power, which is the amount of work done per time. So C is our best bet. Alright, now we're getting to the heavy stuff. An electric motor is used to operate a lift. The motor does this much of work in 70 seconds. What is the output power? So if that's the work done, the formula is pretty simple. Power is equal to work done over time. The work done is 140,000. Divide that by 70, and that comes out to 2000 watts or 2 kilowatts, right? And that makes us answer C. What is the expression given for the efficiency of an AC generator? Well, what is efficiency? It is the ratio of the output over the input, or how much useful energy was converted. So an AC generator is producing electricity, and if it's producing electricity, the output should be some form of electrical divided by input. Now generators take in ever so directly kinetic energy, but there could be a different source of that kinetic energy. But I don't think it's confusing us too much. It's just telling us the total energy input, right? Total input. So I like the answer A. It's giving us it's pretty good. What's wrong with B? Electrical energy output, that's correct, but thermal energy output. Well, if they had said thermal energy input, we would have considered it, but it's not input, right? C is the reverse. D is also just weird, right? So the best answer is A. A small motor has an input power rating of 10 watts and is run for 5 minutes. What is electrical energy? That's pretty easy. We put it in the formula. Power is equal to work over time. Essentially, we want to figure out work. Power will be 10 watts. And time is 5 minutes times 60, because we have to do it in seconds. And the work done is something we have to find out. And I'm getting a solid 3000. Makes my answer D. Probably one of my favorite questions in the entire worksheet, or favorite type, because this seems like a crazy question, but if you apply simple formulas, it just gives you a very solid, consistent answer. A small hydroelectric power station diverts the water from a river. Every second, 20 kilograms of that water flows through a pipe and falls through a vertical drop 15. That's cool. 20 kilograms. I would circle every value if I was you. Vertical drop of 15 meters. The efficiency is also given to us is 0.6. The gravitational field is this much. What is the power output? So let's figure out how much energy is being given to the power station. So it's given to it in the form of potential energy, and that is mgh. So that's given to it every second. So every second it gets a mass of 20 kilograms that experiences gravitational acceleration of 10 meter per second and falls a vertical height of 15. ठीक है. So the total energy the dam or the power station in the dam is dealing with is 3000 joules of energy every second. That's interesting, right? Now, how much of this energy is actually converted to useful output energy? Well, we'll use the output or efficiency formula. So the output energy is efficiency times 0.6 times 3000. That's the input. And it comes out to 1800 joules, right? Pretty cool. So that's the output energy every second. But they're asking for the power. Well, I know the output energy, and this is every second. So I think power should not be an issue. Power is equal to 1800 divided by 1 second, because this is the energy produced every second. So it's still 1800 watts. I don't think you had to put this in the equation. You could just easily figure it out. And the correct answer now is B. This child over here has a mass of 60 kilograms and climbs some steps. He travels a horizontal distance. Like, oh my God, he climbs, right? What is the work done against the force of gravity? So ignore so much information given. What is the direction of gravity? Like that. What is against gravity? Like that. So what is the work done in this direction? Well, the force applied is equal to his weight, right? Which you can easily find out is going to be 60 times 10. You can use 9.8, but you'll get an approximate answer anyway. So 60 times 10 is 600 newtons, right? And what is the work done? Work done is force times the distance. This is 600 times the distance, 1.5. This comes out to, I think, 900. Don't even have to put it in the calculator. 900 joules. Answer is C. Or should I say C? A motor is used to lift a load of 0.5 meters vertically as shown. So it's going up vertically. The load is 400 newton. The power of the motor is 200 watts. And the system is 25% efficient. So much information. How long does it take to raise the load? Okay. The load. All right. Power is that much. What is the work done? Or what is the change in potential energy? Either way, you'll get the same value. So let's figure out the potential energy change. That's PE equals to mgh. Well, the weight is 40 times the height, it is 0.5. That's a small value, comes out to be 20 joules, right? And what's interesting is that the motor is 20 watts, but is only 25% efficient, meaning 20 of those watts, only 25% is being utilized. So what's 20 times 0.25? 25% of 20 is 5 watts. So the actual power you're getting is 5 watts. And the input rating is 20 watts for the motor, but it does 5 watts of work. So 5 watts, let's change our color. Power is equal to energy or work done over, again, time. Power is 5 watts. The work required is 20. Divide that by the time, which we don't know. Time will come out to 4 seconds. That makes our answer C. Alright, very similar question to last time. Alright, so what is the energy or potential energy of the system? It's mgh. What is the mass? This time the mass is given to us like a complicated version of it, or in a complicated numbers, times 10. What is the height? 50 meters. Wow, that looks more like an actual dam. So all right, I'm getting my value as 210 times 10 to the power 6 joules. Now you may ask, why didn't I write 2.1 times 10 to the power 8 or 0.21 times 10 to the power 9? They all mean the same thing. You should know that. It's good practice to keep it everything in 3s, 6, or 9s in multiples of 3. So that, just helps you kind of process it a little better. So if everyone does that, these numbers look a little easier. Because why 3? Well, 3 is just 1,000. 10 to the power 3 is 1,000. 10 to the power 6 is 1,000,000. We already do this, so why not do it here? It's kind of a nice way of doing it. So this is the total energy coming out. And I guess that's kind of it. If I, change the place of the decimal, I'll get it here, and the power of 10 will be 8. So that's our answer, D.